Hey guys, I was unable to make a cool intro, so I'm just going to give you these notes because I know you guys have a lot going on, so let me just give them to you real quick on electric potential, otherwise known as voltage. Those are synonymous. I'm going to use them interchangeably. So voltage is going to be determined or represented by capital V and is given by this equation. It's determined by the charge that's creating it and the distance to the charge, not squared, just inverse. So you might see that this is similar to electric field, but not exactly the same. So it's also similar or different than electric field in the sense that it's a scalar. There is no direction. And it yields potential energy as opposed to yielding force. So potential is different from potential energy, but of course yields or gives a charge potential energy. If you place a charge in a voltage field, it's going to have potential energy in the same analogous way that placing a charge in an electric field yields a force. Of course, an electric field's a vector, gives a force vector. Potential is a scalar. You put a charge in a voltage, it now has potential energy. So that's the secret. That's the cool, important function of voltage, is it gives energy, is related to charges. And we'll see that's intimately related to electric field because this looks a lot like electric field, doesn't it? Right? It's 1 R away, so it's really cool how to intermingle potential and field. And we're going to see the relationship between the two unfold as we do examples. If I have a positive charge, let's map the potential field around it. The distance d away, it'll have a voltage V equal to kq over d. Everywhere distance d away, it'll have the same value. Forgive me for not drawing a nice circle there. Maybe I can redraw that. Everywhere distance d away, it's going to have the same voltage value V. And everywhere distance d over 2 away, it'll have, what is it? Careful. It's closer. So it's going to have a larger value because it's an inverse. The electric field would be 4 times larger. But the potential is not an inverse square law, it's just an inverse law, so it's going to only be doubled. And of course, everywhere distance d over 2 away, it's going to have the same voltage value of 2. And if we go a distance 2d away, of course it's going to be an inverse law. You're going to have a voltage value of v over 2. And that's going to be an isopotential surface. So let me introduce that word, isopotential surface or isopotential line are these rings that form around charge. And of course they decrease like a hill decreases in height. So you want to think of this as like a hill that the positive charge creates where all these values are positive and decreasing over distance as an inverse law, not an inverse square law. So the first key difference with this and electric field is that you do not put a positive test charge to test the direction because there is no direction. There's only a number. Like height, there's no direction. It's just a number. You're at a certain value of height. So if I were to have a negative charge, notice how a negative charge does the exact same thing except that it creates negative values. So here V would be negative kq over d because q is negative. So we're going to have negative V potential surface here. Try that better. Negative 2V here. And negative V over 2 here. And of course, depending on the distance, you're going to have different values, but I thought it'd be nice to do D over 2, 2D, and D. So notice how this gets less negative as you go out and less positive as you go away from this. So there's one more thing I want to show you guys, which is if we draw it like this, where we have a positive charge creating a hill of potential, will it ever get to 0? Well, no, because it's a 1 over r shape, right? So it will asymptotically approach 0 from both sides, and if we have a negative charge, it'll create a well of potential that will asymptotically approach 0 from the negative side. And you can think of the voltage like height, like maybe this is 2V, and this is V, and this is V over 2, right? The farther away you get, the less the height gets as a 1 over r shape. And this is the analogous but negative value. So the key is to think of voltage as height, and what's really cool is the analogy between this equation, QV. So if I put a charge in here, it's going to have potential energy. So if I put like a proton in here, it's going to have potential energy, and it's going to want to go downhill. It's going to lose potential energy going downhill and speed up, gaining potential energy going there. Just like potential energy equals mgh. We'll look at the analogy between height and voltage. It's beautiful. Weight times height yields potential energy in the same way that charge times voltage yields potential energy. So the catch is, of course, what if I put an electron here? Uh-oh. That negative charge screws everything up, right? So it wants to go uphill. It wants to go toward the positive or away from the negative, whereas the proton wants to go downhill toward the negative or away from the positive. So having an electron puts a negative sign here, which gives a negative potential energy for a positive height. So this is downhill, right? This is towards lower potential energy for an electron, because this would be a negative potential energy, and this would be a positive potential energy for the electron, right? Talk about baking your brain, right? So the thing you want to just remember is that positive charges want to go downhill toward lower potential, lower voltage, and negative charges go uphill towards higher potential. And I'm running out of batteries, and this is a perfect place to stop. So a negative charge would be like having a negative mass. Imagine letting go of a negative mass. Those don't exist. It would fly up. It would go away from the earth. It would be repelled by it. How weird is that? So negative charges go the opposite way. Positive charges go toward lower voltage. Negative charges go towards higher voltage. We'll practice this in class. Have these notes ready. Hope that wasn't too bad. I'll see you guys later. Have a great weekend.